In this session, I'm going to talk about understanding the relationships between the continuous variables. We know that the continuous variables are the quantitative variables which can have literally any kind of value. They could accept decimals, all that kind of stuff. So here the main agenda is we'll look at exploring the associations between the variables wherein we will be using the scatter plots. So we'll plot the scatter plots and the different extensions to that scatter plots using R. We will talk about how do I typically plot multiple plots in a single screen. Till date, whatever the R graphs that we are plotting one graph per Excel window, per R window, screen window. Now we will be talking about how do I really combine multiple plots into a single graphics object. Then some interesting graphs with respect to scatterplot matrices. And we will be talking of correlation coefficients as a measure of relationship between the variables. And how do I really understand these kind of correlations and associations, especially in the ordinal data which I collect through the survey responses, through some kind of scales, Likert scale data if I am collecting. How do I really measure the associations in those kind of survey responses? So these are the different kinds of aspects that we are going to look at in this session. So here our major intention, the whole purpose of this chapter is to understand the relationships between two variables and visualize that. Different kinds of graphs which depict the relationship between the variables as well as the kind of calculations and statistics that we can compute on those variables, which will really describe to what level or to what extent the associations exist between them. So let's get started exploring the associations using the scatter plot, right? So for that, let me get the data into R. So I'll be using some retail customer data, right? So let me get that data into R first. So let me use a variable called retail, which would be holding that data. I'll be searching for my CSV file. So this is the path which contains my retail customer data. So let me have a quick look at what is there as a part of that data. So this is where I'll do ahead to understand the first 6 values. So there are quite a few variables here which talks about the customer ID, the age of the customer, much detailed age, right? It's not a rounded off kind of a number. It is the age much detailed. Then I have the credit score of the customers, whether they have an email ID or not, the distance to the store from their home, then how many online visits they have made, how many online transactions they have made, how much of spending they have done online. Similarly, store, how many transactions they have made at the store by visiting the store, how much they have spent at the store. So are they satisfied with the service? Are they satisfied with the selection part? So these are the various aspects that are there for this particular data. And along with that, we could also see the dimension which talks about how many customers have been used for this. So there are 1000 customers responses and the 12 variables have been used in this case. Then I would also try looking at the structure of the data, right? The structure of the data, if I'm looking at, it's a data frame, 1000 observations are there, So the customer ID is an integer, right? It's better that I convert it into a factor, right? No use of it being an integer. Age, credit score are numbers. Email is a factor with two values, no and yes. Then distance to the store is a number. Online visits is an integer. Online transactions is an integer, like this. Okay. So the only thing possibly customer ID, instead of being an integer, I would prefer it being a factor. So this is where I can directly modify the stuff. Retail, so retail dollar cust ID is as dot factor. I'll convert it into a factor. Retail dollar cust dot ID. So now let me look at the structure of retail, wherein now it is converted into a factor with 1000 different levels. Now this is the kind of a data that I have. So there are so now let's start looking at, I would be using the scatter plot, right? So the first thing is to explore the relationship between x and y. I'll use my plot x and y kind of a plot x comma y kind of a command. So wherein, let's say I want to find out the relationship between the age of the customer and the amount that he is spending online, right? I want to find out whether youngsters spend more online, right? We'll talk about online spending, amount that is spent online. So whether there is a relationship between the age and the amount that is spent online. So this is where I can use the simple plot function. So I'll say plot, so x comma y. So x I can set it as the age of the customer, which is retail dollar age, and y is retail dollar online dot spend. Right. So I'm trying to look at the relationship. Okay, so this is the way the graph got designed. Looks like for all ages, majority of the spending is at 0. So it's not giving any kind of a good picture regarding these two. Otherwise, let me try the relationship between the age and the credit score, assuming the numbers are there for everyone. So let me repeat this graph, right? I want to find the relationship between the age of the customer and the credit score. So the credit score is credit dot score, the variable wise. Okay, so this is the kind of graph that got generated, right? So right now it is looking like it's a default graph. I've just used nothing. I've just used a plot function, and this is the kind of a graph that has come. So the default axis is retail dollar age, that is the input that we have given. Here also retail dollar credit score. But the same plot function can be very well improvised by giving so many things, right? Probably if you start looking at the same thing, now I can improvise this graph. I can set the color of this to something. The whole thing I can set the color of it to green, right? Or probably, yeah, I can set the color of my choice. There are a lot of colors that R understands. So we can set the name of the color as red. Then if I want, I can set the limits of both X and Y. So the starting point to the ending point. If I want the limits to be set, I can use X lim. If I want the Y's limit to be set, I'll call it Y lim. So I can give the range, or I can talk about main, which is the heading for the graph. The heading is talking of age versus credit score, right? Then probably X lab, talking about X label, X axis labels. So age is the X axis label. YLAB is the Y axis label, where I'll talk about the credit score, right? And yeah, I can keep, okay, let's keep up to here. So our chart is now modified, right? Now, if required, if I really want to add, right, the mean for X, mean for Y, we can use it through an AB line. AB line, in AB line, it's a kind of a straight line that we are drawing. So if I say H equal to, a horizontal line would be drawn. So based on the average age, horizontal line is for the average credit score. So I'll take the mean of the credit score of the customer. So retail dollar credit dot score. So I'll take H value. This is where the horizontal line would be drawn. So if you want, I can, okay, we'll simply take H equal to mean of retail dollar credit score. So there is a horizontal, so that's a mean value. Similarly, if I want vertically, so I'll set V equal to, so I'll get a vertical line wherein I'm looking at the mean age. I'm looking at the mean age, I get a kind of a vertical line. So these kind of stuff, so I can see in which quadrant, which kinds of values are typically lying. So these are the different kinds of improvisation. So I'm adding, once I have created a plot, I'm trying to add the different lines to the plot, so which are indicating the average age and the average credit score of the customers. Now we can even more improvise the chart, right? The same chart can very well be improvised. We can add a few legend. So color we have already added, X limit, Y limit, they are setting the range for each of the axes. We have set all this. In some cases I can use a CEX. CEX is the plots are either increased or decreased to their natural size. This is the natural size of the plot. Now if you put a value less than 1, they would be becoming that much percentage of the original. If you put CEX value greater than 1, the plots would be increased by that kind of an extent. So that's one more thing that we can look at. Let's say the same chart I modify, right, by adding CEX equal to 0.5. You'll get very small kind of circles. That's the only difference. You'll get pretty small circles. In some cases, if you want to bring in more and more clarity, this could very well be used, right? So this is where we can have one more kind of a lookout like this. Then moving further, I can add extra AB lines. This is what we have already used. Then I can talk about points. Points talking about adding specific points to the chart. If I want to add a few specific points, I can very well add them. Or if I am using lines, I can add some specific lines by setting the coordinates, and legend I can still add, especially here it's a simple kind of a graph, so I don't need to have any kind of a legend. But if I am differentiating it on various counts, it's better that I add some kind of legends as well. Right? Each of these elements, they are added to the plot that is already been created. So I have created this plot using the plot function. So when I'm using these points, they are primarily to add some specific points. When I'm saying AB line, it's adding the lines to the plot. When I'm saying lines, it's adding a set of lines where I'm giving my coordinates. And when I'm saying legend, it's adding a legend. So these are all extra functions that I can give to an existing plot itself. Right? All right. Then let's move forward. Now, a few more interesting points to bring out here. Right now, all the points are simple. All of them are pointing in one direction. So let me first remove off the CEX. Let them show the normal size itself. So this is what is our normal plot. Now what we are saying is, if I want to color code them or give a different shape to them, right? I want to define color. I want to define different shapes as different variables. For different variables, I want to give different kinds of colors, right? So let's say let's define two different colors. So here what we'll do, we'll use some, we'll use this email as a variable, and based on this email variable, so we want to differentiate the color and even the shape. I want to differentiate both the color as well as the shape based on the email variable, right? So let me do something. First, let's give different colors, right? Let's say, what are these? Credit score colors, CS dot color. I am calling credit score colors. So let's give two different colors, one for people who have email versus one for people who don't have email. So I'm talking of green and blue. Right, these are the two colors I'm interested in. If you really want to give different shape also, we have to use PCH. So that's where I'll talk about two different shapes, two different PCHs. You can give any number from 1 to whatever, 1 to 100. So we'll talk about each one denoting a different kind of a shape. So let me call 1 and 2. So they are the different symbols of R, the PCHs. So let's see, we'll get different kinds of shapes. So now I want to typically look at the different colors, right? The different colors associated with the plot. I'll be using this. So I'll do a plot based on the same, right? So we'll talk about the plot. Let's say here we will try to find a plot between two other things. So here let me take an example. Now that we are taking email, whether the customer is having email or not. So I want to compare between the store spend versus online spend. I want to really see if a person who is spending more at the store does not have email, right? Is there some relationship between the persons having email versus the amount of spending they are doing online versus retail? So this is what I want to try out. So that's where I am taking retail dollar store spend, right? How much they are spending at the store versus retail dollar online spend. How much they are spending at the store versus how much they are spending online. So I'll have to use the color differentiated now, right? So when I have to differentiate, the differentiation should be based on the email, right? So I have taken CS dot color. There are two CS dot colors. So this is what I have to take out of the CS dot colors. I want to give them based on the email ID. Retail dollar email. So retail dollar email means there are two values associated with the email ID, right? So the levels of it will be shown. So it's as good as it's a mapping that is being performed. No would be given the green color. So yes would be given the blue kind of a color. The same logic I can put PCH is equal to. So I can really set it here itself. So because I have given this CS dot color. So out of this matching with the retail email, I would be getting the colors. Similarly, because I have given PCH as two values, I can get CS dot PCH. I'll take a subset of the CS dot PCH, wherein again I can take retail dollar email. So for those who have yes, one value would be picked. For those who have no, the other value would be picked. Now I can very well set my main. I'll call it age versus oh sorry, this is not age versus. So store spend versus online spend, and X label, Y label if you want I can give, otherwise let me ignore them for the purpose of understanding of the graph. So now you could see there are blue triangles, right, as well as green circles. So because circle is with 1 and triangle is with 2, PCH value 1 means it's a circle and PCH value 2 means it's a triangle. So this is the typical kind of a graph that we are receiving right now when I am trying to plot these two values. And if required, yeah, we'll talk about adding the legend here, right? So let me keep adding the legend. So the first input into the legend is where do I want the legend to be plotted. So I can very well talk about, let's say this top right corner is more or less free for us. So let me use the top right as the position of my legend. Now in the legend, if I want some kind of text and some kind of variable both to be plotted, then I can use my paste function. Paste function will do both the variable part as well as the constant kind of part. So email, let's say I want to put the fixed part saying email ID this. So email ID this is what is the fixed part I want to put, and here I want to use the levels associated with the email. So for one person it would be shown as S, and for the others it would be shown as no. So the levels I'll directly link it levels of the email. So email ID colon no, email ID colon yes. So these are the two things that are going to come as a part of the legend. And from here I can set my color, which is cs dot color, and I will also set pch is equal to cs dot pch. So this is going to do this kind of legends. Circle email ID equal to no, triangle email ID equal to yes. So probably once the chart is plotted, we can very well go and do this kind of legend. Of course, this legend has to be done manually. There is no automated way of creating this legend using the base functions of R. So this is what I think we have looked at. We have created a legend, given the location, top right, top, bottom right, bottom, bottom left. All these are the typical locations. Otherwise, I have to give the coordinates of X and Y. Given the legend, in the legend we have used the paste function, especially if we are combining the constant with some variable value. So that is how we are using the legend. Now in some cases, it might very well be possible that I would like to plot the data not on an original scale but on a log scale. So I want to take the logarithms of the values. Now this is where I can use this extra argument in the function, especially with the skewed data. In this case, you could see lots of concentration is here itself, right, where you are not able to understand the overall data at all. So I don't want those kind of people who have not spent literally anything. So this is where I am taking the log scale. So I can very well consider when I am taking the log scale, I want to specify whether I should take the log only for X, right, only for X values. Then I said log equal to X. If I want only for Y, I'll set log equal to Y. If I want both X and Y to be plotted on a logarithmic scale, then I'll set log equal to XY. So the same chart I can improvise by setting log equal to XY. XY means take the logarithms of both X and Y. So the moment I take log XY kind of a chart, this is the kind of distribution I am getting to the chart. Rest all remaining the same, right? I can very well take the logarithm of XY. Of course, here the problem is there are so many zeros. So log 0 is undefined. So one more way of doing it is instead of taking the values as it is, I'll just increase them by 1 so that zeros will be converted into 1 and their log values will become, otherwise they are all shown as NAs and they are omitted. So if I just increase by 1, their logarithm values are going to be 0 and I'm going to get a plot more like this. So this is the kind of a plot that I'm receiving, right? It's better the CEX can be reduced here. The chart is looking very cluttered. This is where the CEX will have an important role to play. I'll set CEX equal to 0.5 so that now at least some kind of plots are observed very clearly. The blues and the greens are segregated quite comfortably out here. So that's how we can use the scatter plot. Now, in some cases, it might very well be necessary that I have to combine the different plots into one single graphic object, right? If I want to talk about, let's say, multiple things, I want to uh, I want to look at the distance from the store, right? I want to track a few things based on the distance from store. I want to take this as an input, see what is the kind of relationship that is existing with respect to store spend and with respect to online spend, right? How is the distance from store impacting the store spend and online spend? This I want to take it on a regular scale as well as on a log scale. I would be interested in taking the spend on a regular scale as well as on a logarithmic scale, and I want to really plot these four charts, and I want to look at these four charts side by side. Till now, whatever is the graph that we are getting here, we are able to see only one graph at a time. So if I want multiple graphs to be viewed on one single screen, this is where I can take the help of this function par, where mf row is set to the dimension part. So x comma y. So it will plot these many charts. So it is, when I say 2 comma 2, 2 rows 2 column, the charts would be plotted as 2 rows 2 column. So let's try this. First let me set par mf row equal to c2 comma 2. So this means now my chart window will be resized in such a way that I'll get first chart here, second chart here, third chart here, and fourth chart here. So let me do the plotting. Once this is done, I'll take retail dollar. So on the x-axis I am taking distance to store. So let me use distance dot to dot store. This is the name of my variable. And let me also take retail dollar store spend. Right? I'm just taking. So the main and all, let me you can very well create them. You can give the labels, x-axis and all, but I'm here more focusing on only how to display multiple graphs in one single object. So this is what is showing the retail distance to store versus the retail store spending. So probably people's whose distance is much higher from the store, their spending is very less. People who are very close to the store, who are staying very close to the store, looks like they are spending very heavily at the store. Some such kind of a pattern is being observed. Now the same thing if I look at online spend, a slightly more or less a similar kind of a pattern is getting represented. Even those people whose distance is too long from the store, very few of them are spending more online also. Even here also you could see the online purchases are higher toward the lower side itself. But for quick track, we would like to see on a logarithmic scale. So let me put this as +1 and let me set log is only y. Right, distance also I want to take. Okay, if I'm taking the distance also on the logarithmic scale, then log xy. So this is the kind of a graph that we are getting. So distance, if it is higher, on an average we are seeing that their Store spending is going lesser, which is what we could see in a general kind of a scenario. And if I am looking at online for this, when I am looking at the pattern for online, it is not that kind of an evident. At least in case of store, I could see a kind of a decreasing trend, whereas in case of online, it is looking more and more flatter. If the relative distance to the store is much higher, I could typically see on a logarithmic scale also, I could typically see that the graphs are pretty much flatter. So we can actually combine the multiple graphs and we can showcase them like this. And if I really want to go back, I can, instead of two by two kind of chart plots like this, if I want one single plot, again I can go to my par MF row, setting it to 1 comma 1. If I set it to 1 comma 1, again I am going back to my normal graph itself. So this is one more aspect that we can be comfortable with. Then moving on to the next part, where I would like to spend some time discussing the scatter plot matrices, where we are trying to do the scatter plots for various pairs of data, right? Not just with one pair, for almost different kinds of pairs of data. I want to come out with a scatter plot matrix, right? So this is what we would like to use. There is a car package. Car is it's a kind of a companion to applied regression. CAR stands for it's a package that has been created, companion to applied regression. So that is what is the meaning of the car here. So we have a car package. Within that car package, we have a scatterplot matrix, which has much features associated with providing a scatterplot matrix, and we can actually use the pairs function from the base R as well. So we can actually understand these two things. So first we can use the pairs function of base R, and based on that we'll move on to the usage of scatterplot matrix, see what kind of differences that they are bringing to the start. So let's say I want to do the pairs for the entire retail, right? I want to do the pairs for the entire retail. So this is what is a scatterplot matrix that would be plotted. So we are giving the pair, if required, if I want all the values, I have to give it like this. But if I want only a few specific variables, I have to give them through a formula. Let's say I want only, so I have to start a formula equal to, put a tilde sign. Let's say I want to give the age, I want to take credit score, I want to take distance to store, and I would like to, let's say, go with online spend and store.spend. Let's say only these variables I want. Each one of them, sorry, I have to join them through a plus, not through comma. So I have to join them through a plus. So that's it. And I have to, because these are from a data store, from a data frame, I have to give data equal to retail. So it gives the scatter plot matrix only these five variables. So it's nothing but it's a separate scatter plot for each. So you could see age versus right, age versus credit score. This is the scatter plot. Age versus distance to store. This is the scatter plot. Some of them may have a meaning. Some of them may not have a meaning. So it's a scatter plot between two variables, and within the diagonal there is nothing much. So that's where only the names of the variables have been highlighted here. So in some cases the relationships are much stronger. You could see here the relationship is more and more upward sloping kind of a relationship, whereas in some cases the relationships are very flat. So such kind of understandings we can very well develop by looking at this entire. So if I'm trying to plot the whole stuff wherein I'm getting all these, so here I could see at least between some variables the relationships are pretty much stronger. Online visits versus online transaction. It's a very upward sloping kind of a relationship. Online transactions versus online spending. Right? The higher the number of transactions, the higher the amount of spend. So some of them are looking very strong in terms of relationship. In some cases, the relationships are more or less flatter. You could see here, okay, customer ID has no meaning, so there is no point in looking at the customer ID. But age versus online credit score, it's slightly upward sloping. But age versus let's say online visits, it looks more and more flatter. All these things are looking more and more flatter with age. So some of them may not give us any kind of understanding to start with, whereas in some of them I can very well go ahead with making a lot of meaning out of each and every aspect. So this is the typical pairs function which is doing the scatter plot matrix of the data. But as I have said, apart from the pairs function, if we have the car package, we can use the scatterplot matrix function, slightly additional set of details that are there. So what I can simply do is you can install the car package. It's already installed on my system, so that's where I can load. I can simply load the car package by using the library. Okay, so then I can use my scatterplot matrix function. I'm using my scatterplot matrix function. I can use it for the whole retail again. So you could see a small difference in the way it has presented the information. Slightly additional amount of detail. The overall scatterplot matrix function, it is taking this kind of detail. So on the diagonal, we could see in this scatterplot matrix, we are seeing some kind of the curves more or less similar to your histograms, but more and more density kind of curves. We are getting different kinds of density curves being plotted on the diagonals, whereas the earlier one was showing more and more associated with just the name of the variable, whereas here apart from the name of the variable we are getting something similar to that of histograms, or probably you call them as density plots. So the scatter plot matrix is producing some kind of density plots which is showing the distribution primarily for each of the variable, right? So it looks like age is more or less normally distributed, credit score is more or less normally distributed, whereas many of the variables are skewed. Looks like many of the variables are skewed to the right? So you have a large number of variables extending towards the right. So there's a lot of skewness that is present in majority of the graphs, and you could see the green lines across. The green line is showing the linear fit, right? If a kind of linear fitment is typically drawn between the points, so there is a scatter plot, and based on the scatter plot, a linear fitment line is also shown. The green line is a kind of a linear fitment line, whereas the red lines that are typically being shown, red lines, red curves, they are the smoothened fit line. So here if I am looking at the green lines are the linear fit lines, whereas the red ones are smoothened kind of fit. Smooth fit kind of lines and their confidence interval. So you could see the light shaded ones, they are their confidence intervals, the high upper confidence interval versus the lower confidence interval. So it's a smooth curves that are being drawn based on the points, and along with them their confidence intervals are also typically plotted. So when I'm doing this kind of red lines with their confidence intervals, so it's a kind of thing that suggests the extent to which the associations are linear. Look at let's say age, right? This is the age versus let's say distance to store. Look at this one, age versus distance to store. The line is looking pretty flat. The red line is looking pretty flat, which means there is hardly any kind of association between these variables. Whereas here the red line is looking pretty much up, which shows that there is a strong linear, positive linear relationship between the variables. Now, but if you look out for email, which is a factor variable here, which is having two values S and no, probably the scatter plot is not good for it. It is showing the list here, it's showing a list of values here, a green line is shown somewhere horizontally. So this is literally not a kind of a useful function when we are primarily looking at the factor kind of variables or binaries kind of variables. In this case, to improvise the graph a little bit more, right, we have another package. This is what I have highlighted here. We have a package called gpairs, and within that gpairs package we can use the gpairs function, which is producing a scatterplot matrix, and interesting visualizations are there for both discrete as well as continuous variables. Because the scatter plot is not ideal for discrete variables, so we are looking at this particular package primarily, which is capable of providing better visualizations even for the discrete variable. So here the only limitation is it does not accept the formula. If you see earlier, we have given a formula saying formula equal to, with a tilde sign, we have given the list of variables separated by plus. But here I have to give the column numbers only. I can't give the formula as an input. So let me see how we can typically go ahead with that. So I have to install the package. I'll install the package called gpairs. I'm installing the package gpairs. Okay, so once I have installed it, I'm loading the gpairs package by using the library, right? So from here, I'll do the gpairs function to plot the scatter plot, but the input is retail. I'll take all of them. So if I look at, this is the kind of a plot that is coming out when I'm using the gpairs function for retail. The customer ID ignore, probably let me do it only for a subset where I'm taking all the rows but columns only 2 to 10. I'll ignore the customer ID. So this is the kind of a graph. So in case of age, there is a kind of a histogram that is being shown. So for each, even the credit score. So there is the histogram kind of stuff that is shown. And in case of email, there is a kind of a bar chart that is typically plotted, right? And I could also see in case of email, there is a kind of box plot that is plotted, right? So slight improvisation here. So for the discrete variables, I am seeing a box plot being plotted. So when it is constructing all these kind, it is primarily determined depending on the kind of data types that are there in the R. Based on the kind of data types that are present in R, it typically creates the appropriate plots for that particular kind of data. So we don't have, I mean, this is purely based on whether we are supplying a factor or an integer or a numeric or what kind of variable into this gpairs function. So primarily in this, the key functions that we have used, if I want to visualize between the various relationships between the various pairs of data, I can use the pairs function from the base R. I can use the scatterplot matrix function from the car package, especially if my data is pretty much numerical kind of a data or integer kind of a data or a numeric kind of a data, then probably this function is very good. But if I have some kind of ordinal kind of a data, gpairs kind of a package with a gpairs function is much more appropriate compared to your scatterplot matrix function, right? So these are the different kinds of pairs visualization that we can do. Now, moving further. Till now we have looked at the relationship between the variables in a graphical form. Now, we'll look at the kind of relationships that are existing between them in the form of single numbers. So correlation coefficient is one such kind of a number which assesses the relationship between each pair of variables, right? I can use correlation COR as a function in R, which can assess the level of correlation between the variables. So if that value is 0, it's a very clear indication that there is no linear association between the variables. So my scatter plot would be looking more or less flat. And value wise, it can have any kind of numbers between -1 to +1. And typically, for people who understand the formula, correlation is computed as the covariance between the variables divided by their individual standard deviations. So that is what is the typical formula for correlation. Though there is nothing called which is when is the correlation strong and when is the correlation weak, some kind of rules of thumb that are there based on what Cohen has given. But the Cohen's rules of thumbs very clearly make an assumption that the variables are normally distributed. When the variables are pretty much normally distributed, then these rules of thumb can very well be applicable. But if they are not, then probably we have to rethink of something else. Like we have to transform the variables to normal, wherein we can do some kind of logarithmic transformations or some such kind of transformations, and then check for the correlation between the variables, right? So such kind of things have to be typically performed. But when the variables are very much normal, I can really see that if the correlation value is around 0.1, it is typically treated as a small or a weak kind of correlation. And if it is 0.3, I talk about it as a medium, and anything above 0.5 is typically taken as a kind of strong association, linear association existing between the variables. So we could typically find out the correlation, let's say between, we'll take for all of them because we can get it for the pairs. I'll take the correlation for retail. Okay, there is a numeric. So we have some variables that are not numeric. So we'll take correlation wherein we'll take retail dollar age and retail dollar credit score. So it is 0.25. It's not that strong. But correlation between, when we saw the graph, we have seen that these are all very much upward sloping kind of stuff. So I want to see the correlation between retail dollar online dot visits, comma retail dollar online dot spend. Yeah, this is looking pretty much high, very close to 1. It's showing 0.98. Now this is where the correlation is a good indicator of the strength of relationship that is existing between the variables. And the way we are trying to find out the correlation, as I have already indicated, it is scaling of covariance by dividing by their individual standard deviations, right? So that is what is typically being performed. Then we can really do the correlation matrix also. So I'll take the correlation. I require only numeric variables. So that's where out of the retail, I'll take the columns. So I don't need the first column. First column is the customer, so I don't need it. I'll take columns wise. I'll take the second column, the third column, fourth is email. I don't want it. 5, 6, 7, 8, 9, 10. And 8, 9, 10. 10 all, 9 and 10 also are the satisfaction levels I may not be interested in. So let me take 5, 6, 7, 8 itself. So 5 to 8. So these are the columns I'm more interested in when I'm taking the correlation. Okay. Yeah, I have to close the bracket. So this is what is the pairwise correlation. So I could see that the numbers are pretty small with respect to age, right? All these are almost negligible kind of values. And what about the store spend? Store spend is also a variable. So let me take 9 and 10 as well, right? So let me take 5 to 10. Okay, so yeah, age has not much of an influence except for credit score. The same is the goes with credit score. But yes, a little bit the distance to store is much higher. I could see that the store transactions are slightly lower and store spending is also on the lower side. Online visits is having very strong relationship with the online transactions and online spending. Again, online transactions are also having similar. Store transactions are having a good relationship with store spending. Right? So these are some places where the relationships are much stronger. And so we can very well understand where the association between the variables is much stronger and where the association is much weaker. So we can take it in the original form or we can even take it in the logarithmic form as well. And in some cases, even a correlation test may have to be performed. Right now, this is a ballpark way of estimating the correlation and saying that whether the correlation is good enough or not. But if I want to go with it statistically, right? Empirically, the rule of thumb is okay enough. But if I want to check for the statistical significance between the variables, I should go with core.test. Core.test is an indication of a correlation test. So what we can do is core.test. If required, I can take for all of these. I'm not sure whether it takes the whole pairs. Okay, so it requires pair of values. So let me perform the core.test wherein I am taking retail dollar age, comma retail dollar credit dot score. I want to find out the correlation test between this. So this test is nothing but Pearson's product moment correlation. In this test, the null hypothesis is the correlation equal to 0. There is no linear association between the variables. The alternate hypothesis is correlation is not equal to 0, which means it's either positive or negative. So you look at this, the p-value, the first thing you associate is p-value, which is 2.22 into 10 to the power of minus 16 less than 0.05. When it is less than 0.05, your decision is in favor of alternate hypothesis. So which says the correlation is not equal to 0. Now based on that you are checking out what is the correlation. It is 0.25. So it's a positive relationship that is existing, and the 95% confidence interval for this correlation is anywhere between 0.195 to 0.311. So definitely it is not 0, right? If 0 is not present in that particular interval, then it says that the correlation is significant, and it does not include 0. The association between the variables is statistically significant. Now I'll apply my rule of thumb and say yes, it is medium because it's somewhere close to 0.3. So I can very well say weak to medium kind of a relationship that is existing between the variable. Now, the same way we have gone ahead with the correlation matrices, right, wherein I can take between all the pairs at once. So in the diagonal I could see all are ones, because the correlation between the same variable with the same variable is always 1. So if at all if at all my data is having NAs in the data, right? Probably if I had included the same correlation, not for 12, let's say not for 10, even up to 12 if I have taken, then my correlations would have shown NAs across, because there are a few NAs as a part of service satisfaction, there are a few NAs with respect to selection satisfaction. So in this case, if I want my correlations to be computed only with the available values, I can set this additional argument as a part of my correlation function. I'll say use equal to, and I can give complete observations, only the complete OBS, complete.obs. So the same correlation I set use equal to complete.obs. Yeah, it has to be in double quotes. So I give complete.obs. So then only based on the variables that are already available, it would typically give my overall correlation computation. It takes only those variables which have values and it ignores those variables, and based on that a revised computation is typically performed. So that is one more thing that we can look at, especially if our data is having so many NAs inside it. Then another interesting way of doing the plotting of the correlation is we have a function called corplot.mixed, and that is from corplot package. Corplot is nothing but the correlation plot, right? So I can very well use the correlation plot kind of a package. So let me install that package. So I am using this corplot package. So let me have a library. Let me load it. So I'm loading this corplot package. Within that I have a function called corplot.mixed. Right, this is a corplot.mixed as a function where I want to, so here the input, now if you see here, uses the correlation matrix as the input. So I have to get my correlation matrix. So this is where I am using the cor, which is the variable of corplot mixed, where I will use the cor function, the correlation function of the base R, where I am doing it on retail dollar, all my retail, I'm taking all my scale variables, so all the rows, and the columns wise I'm taking column number 2, column number 3, and then column numbers 5 to 12. 4 is email, so I don't want to use it. So I'm using my cor function. So here it's not square bracket, here it is the typical bracket. Cor is a function. So I'm doing the cor of this data, and at the same time within this cor I want to make sure that NAs don't come. So that's where I'm using use equal to complete.obs. I'm getting only the completed observations. Right, and probably here there are a few more additional variables that are associated with the cor plot. Right, so this is for the cor part. So within the cor, retail and use, so the correlation function is done here. Then The other inputs relating to the core plot. So the upper, we'll talk about this. The upper is a variable where I can get the different shapes. So we will get it in an interesting way here. So the shape I can very well specify, and if I don't specify, the default shape is going to come. But I can specify a few shapes, and ellipse is the most commonly used kind of a shape here, right? And so once I give this information, we'll see what is coming out. So this is the typical plot that is coming out. You could see here the lower triangle. So it's a triangular kind of a stuff. The lower triangle is clearly specifying the three the correlation numbers, right? 0.98, 0.99, which are in dark. The medium ones are shown in a light colored blue, and the red ones are shown with a negative. So we could see different kinds of color schemes. By default, you could see -1 to +1. This is the typical kind of a color scheme that is applied. So you could really make out between which ones the correlation is pretty strong if the relationship is much weaker. So on the lower part of the triangle, it's the numbers, and on the upper part, it is the ellipse. And that ellipse, the more the correlation, it is becoming more and more like a straight line, but almost no correlations, they are becoming closer to a kind of a circle. So it is easy to visualize all the correlations in the data. I can look at the numbers on one side, which is the downside of the triangle, and at the same time I can also look at their corresponding plots. So the correlations which are very close to zero, they are more and more circular in nature, and if they are very much away from the zero, they are producing lots and lots of ellipses. And probably we can very well set the colors also, right? If required, we can very well set the different kinds of colors, but I require a color panel for it, right? Because across, right from the left to the right, it's not that 3 different colors or 4 different colors. So I can use some kind of color panel. This is the default color panel that is being used, but I can very well resort to. There are some packages which are exclusively dedicated to different kinds of color panels. So if I can very well install any of those packages like Gplots and all, where we can get the color interpolations kind of thing also perform. But here, just to understand, the correlation plot can be done even through this kind of a mechanism as well. Very interesting way of presenting. The correlation numbers are shown in the bottom half. The correlation graphs in circles and ellipses are typically shown in the top half. And to the same chart, let's say I want to showcase what the variable names. Here the variable names are not being present. So this is where what I can do is, I have one command here. Probably you can do all these things using your question mark. Right, once you know the name of the function, you can very well do a question mark and typically see what all it can do for us, right? So I can very well talk about TL dot position, where I am trying to set where I want my text, right? So I'll using TL dot position, wherein I am using LT means left to top, left and top. So I'll get the names of the variables here, the names of the variables here. So this is the way I get the names. So if I want to improvise the chart a little bit, these are the some other kinds of things that I can very well do. So if we want some kind of color panels, we can very well use those color panels, right? We have, let's say I want to use some kind of color panel for this itself. I'll use a package called Gplots. Gplots contains a lot of color panels. So let me use the Gplots package, right? I'll just show you how do you use that color panels from that package. So it creates a kind of an increasing to decreasing kind of scale. If I am using gplots as a package, and let me load that package. Now the same correlation, what I can set, now I have the color panel with me, right? So the same function, I'll extend it with color, where I'll use color panel as a function. Within that color panel, I have to clearly specify what are the three colors that I'm going to go with. So it's a kind of a changer. Then I'm let's say going with red for something right, and then gray for in the middle, and probably green for something positive. Let's say such kind of a color position is what I wanted to set. Unexpected symbol. What has happened? Oh, I did not put a comma out here. So after LT, I did not put a comma. Yes. So now you could see your graph is slightly different. It is showing gray. So all those in gray. So it is like it is trying to make it out from -1 to +1, red to green kind of transition. And in the middle, it is talking of a kind of 0, which is with a gray color. So the ones which are slightly negative are shown with a mix of red and gray. The ones that are very much positive, they are shown with a kind of a green color. So this could make your graph slightly more visible and interpretable. In some cases, rather than using the default, using these kind of color panels can typically make a lot of difference. So this is what is the core plot mix kind of a package. Numerical values of the correlation are shown in the lower triangle of the matrix. Upper triangle is displaying the ellipses. I can use the colors for the positive and the negative, where I am using the color panel from the gplots package. And TL is LT, shows that we are looking at the variable names on the left as well as on the top of the matrix. So these are some more interesting things that we can talk of when we are using the correlation coefficients. Then in some cases, it might very well be essential that I may have to transform the variables, right? By default, the correlation may not be that great, but if I do the transformation of the variable, the same thing, if you just want to see the core function, log, if I take retail dollar age versus log retail dollar credit dot score. I'm just taking the logarithmic transformation between the variables. Okay, here it is not too much of impacted, it's the same 0.25, but in some cases the correlations could be different. Let's say we are talking of the distance to store versus the spending, right? Let me take correlation retail dollar distance dot to dot store comma store spend. If I'm taking the correlation as it is, so you could see the distance to store versus the store spend, it is showcasing minus 0.24, right? So there is a negative, that is what it is being displayed as. Now let's say I want to take with respect to 1 by distance. The same thing, instead of taking distance to store, I take 1 by distance to store versus the store spend. I could see that the correlation has become 0.43. So when I'm taking, instead of taking the values as it is, if I have done a reciprocal kind of a transformation, the correlation is typically going up. There's a good association between the variable. Similarly, if I say 1 by, I take the square root of the distance to store, it's coming out to 0.48. So which means I could better say that based on my observations, the retail store spending is inversely proportional to the square root of the distance more heavily. So if the distance is going higher and higher, the amount of spending that the person is doing at the store is typically going down. And my plot also reveals a completely different kind of a picture when I'm doing the transformations on the data. So that's one more thing that we may have to do to understand the associations between the variables, right? In some cases, it is very much essential that I perform the transformation before I really understand the relationships between the variables. Now, this is where, just for an understanding purpose, for the marketing related data or even the finance related data, if I'm talking of sales, revenues, household income, prices kind of variables, the most common transformation that is applicable to them is the logarithmic. If I'm talking about the distance, better to apply the reciprocal or 1 by x squared square root of x kind of transformations, or even a logarithmic. The more and more the distribution is having a right tail, means positively skewed kind of data, better apply the square root transformation or a logarithmic transformation. But if it is more and more negatively skewed kind of a data, better apply a squared transform. Of course, these are all approximate kind of transformation, nothing to be exact. But if I want to get the very best kind of a transform, then we are talking of the usage of Box-Cox transformation. And this is what is the Box-Cox transformation. Yi to the power lambda typically is yi to the power lambda minus 1 divided by lambda. If lambda is not equal to 0, and if it is 0, we'll be taking as log yi. So that is the typical transformation that we can perform on the data to get the best kind of value close to normality. So, but here we get a very interesting function, which is the power transform function present as a part of the car package, which can automatically find this lambda value. Right, let's try it out. What could be that lambda value? Already the car package is loaded. So I'll say power transform, right, which will give me that particular lambda value. Let's say I want to do it with respect to distance to store, right? Retail dollar distance dot to dot store. So it says the lambda value that is more appropriate in this case is minus 0.03. Right? So it's a straightforward. Let's say I want to find out the power transform, the lambda value, to make it more and more normal. I want to use the power transform associated with retail dollar age. It says the power transform is 1.03. The more and more the data is close to normal, I could see that this lambda value will be very, very close to 1. Right? So we could clearly see, we can find out what is the kind of lambda value. Based on that, we can apply the power transform. So we can get the lambda value from there. So the lambda is given minus 0.03 in case of distance to store. So I can very well take now the correlation with respect to distance to store, as well as probably now I can look at the kind of correlation distance to store versus store spending. I can take both of them normal. So earlier when I took this 1 by square root of distance, this is the kind of correlation that was existing. But now I'll try to make it as much normal as possible. So let me take even the store spend also the same way. Right, instead of distance to store, let me take even the store spend as well. And after that, let's see the correlation. What has happened? Power transform. Okay, it has to be strictly positive because there is a possibility of zero values being present. The power transform is not working. So let's do a +1 for the store spend. So here it is giving that the value is 0.11. So what I will do is we'll create two variables now, right? The transformed distance. So which is coming out, I'll take the coefficient from that power transform function. So I'll take the coefficient from this power transform function. So this I'll call it as trans.dist, transformed distance. I'll also call transformed store spent. This also I'll take as the coefficient of this one. This is the transformed store spent. So if you just see what is the values that are coming, transformed distance, it's coming out as minus 0.03. The transformed store spent is coming out as 0.11. So these are the values that are coming. Now we'll have to use another value, another function called BC power. BC power is performing this Box-Cox transformation by using your lambda value. So that is where I can, if I want to find the correlation between both of them, so I have to use BC power first to transform it. So I'll say BC power of retail dollar distance to store. This is being transformed so that the data comma lambda. Lambda is trans.dist. So this is this lambda is applied on the data, and the BC power is actually transforming the data using this Box-Cox transform. The same logic I can use now. BC power, the second one, I'm taking retail dollar store spend +1 because I did not want zeros. I'll do it as store spend +1, and the kind of variable that we are using is trans.ss. So between these two, these are two normal, close to normal kind of a variables using the Box-Cox transform. So based on that, I'm trying to find the correlation. It comes out that the relationship between the variables is minus 0.46. So it is still a negative relation, but this is the best possible relationship that could exist between these variables. So the Box-Cox transformation is talking about different kinds of lambdas, right? Just to summarize the stuff. So instead of we iterating through different lambda values, we can very well use the power transform function from the car package, which will automatically find the lambda value. Based on that lambda value, use your BC power function, which would typically apply that lambda to the series of data and compute the new data values. And based on that, you will get your transformed variables. And based on them, if you really want to do some kind of correlations, you perform correlations on them. So if your data is very, very close to normal, you will find the lambda values to be very much closer to 1. So that is one more thing that we have to understand as a part of the correlation coefficients. Then one more aspect that we want to look at in this session is the associations in survey responses. Especially if you see the survey responses, they are more or less a 5-point scales or 7-point scales where the variables are more or less ordinal in nature. We talk about extremely dissatisfied, dissatisfied, okay, satisfied, extremely satisfied, some such kind of a ratings which are on a discrete scale. So when I'm trying to do a visualization of that using a scatter plot, it really does not give any kind of a meaning for me. So probably here, let's say I want to take the simple scatter plot between two such variables. We had sad.surveys and sad.selection. So the satisfaction with respect to service, with respect to selection. So let me call sad.service and let me also take retail dollar sad.selection. Let's say this is the plot I want to take. So it's simply giving some kind of quick plot. So okay, probably there are nothing here. That's the only thing I can make out. There are nothing here. So people who have given 1 on service satisfaction, they did not give 3, 4, 5. No one of them have given 3, 4, 5 on the selection satisfaction. Similarly, so people who have given low on service satisfaction, they have given equally low on the selection satisfaction as well. Right? But people who have given high on one, they have definitely given high on the other as well. So only that is the kind of information that we are getting through the simple plot. Now, this is where I want a little bit, if I want more and more of concentration, right, where what kind of people have given low. Here it is doing one plot per each observation. So, but if I really want to know which combination is very highly selected by the people, where it is very strong, where it is very weak, then this is not able to say because all the circles are looking more or less similar. Now, this is where I want to use the jitter function. The jitter function, it is adding a small amount of random noise to each response. So because of that, what happens is instead of one point here, you will find so many points in and around this particular area. So each point is slightly disturbed here and there, and based on that, it is primarily creating number of points which are around that particular point itself. So the moment I am adding a jitter to my data, probably the graph looks slightly different. The same plot function, everything remaining the same. Instead of taking the variable as it is, I say jitter of this. Especially if I want to add some random simple noise around each variable, especially this we do with ordinal data. If I add some such kind of a jitter around it, probably this is how the plot is getting modified. So I could see things are very, very concentrated here, 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 here. Very few out here, almost only one out here, who have given 5 on service satisfaction and 5 on selection satisfaction. There's only one person. Very few 4 and 5. Right, again very few 5 and 3s, but the major concentration is 3 and 3, 3 and 2, 2 and 3. So these are looking like very common kind of selections among the individuals. So you could really see where things are very strong by going ahead with this jitter. Right, so moves the points away from each other. How many responses occur at each combination? It's very clearly analyzed. So very interesting thing for your survey responses, getting a kind of a jitter to your plot. Then another important function that helps in associations between the survey responses is the psych package having a function called polychoric. So let's install the psych package. I think it should be installed in my system. But yes, let me quickly look at it. So let me do a library of psych. Okay. So polychoric. So we have a different kind of correlation coefficient. Polychoric is a different correlation coefficient, especially for ordinal responses, where the responses are pretty much ordinal in nature. I can go with a polychoric correlation coefficient. What this makes as an assumption is, okay, when someone is giving a 2 or a 3 or a 4 or a 5 on a Likert scale, they have some kind of continuous values in their mind. But because they can't give that continuous value, they try to find the closest thing which is associated with these values and then give either 3 or 4 or 5. So this is what is polychoric trying to do. So it creates some kind of hypothetical continuous variable based on this kind of numbers or ratings that the individuals have given, and based on that they try to compute the correlation between the variables. So let's try. Let's check out where the NAs are not there. Right, probably what I can do is I'll do an NA.omit altogether for understanding this. So let me simply take response, or probably, yeah, I'll take the response as 2 variables only. So out of the retail, I'll take the subset of retail into the response, wherein I'll take only 11 and 12 columns. Only 2 columns which are talking of both the satisfactions, right? So I'll take the response. So there are 1000 responses with all these things. So what I want to do is I want to do an NA.omit. So I'll take a response wherein I'll omit all the NAs. NA.omit will omit all the NAs. So now when I look at the response, so wherever the NAs are there, they are omitted, rest all are being taken. If I take simply the correlation on the response, it comes as 0.58 right now. The correlation of the response is coming out as 0.58. But let's say now I want to find out the polychoric. Right, polychoric is a different correlation, as I have said. So let's say I want to find the polychoric again on the response. This time I could see that the correlation is 0.62. When I am taking the polychoric here, I am looking at the correlation being 0.62, slightly higher compared to a 0.58 that is coming here. So along with that, it's also giving a kind of a tau. So these are the kind of cutoff point, which means it has actually internally converted these scores into a numeric values, and the scores are being given. So anything like, let's say minus 1.83, it has actually standardized these values. So anything below minus 1.83 has been given a value of 1, minus 1.83 to minus 0.72. So those are the kind of values that are visualized for. So it is like those people who have answered a response of 1, they have been given values of minus 1.83 and below. So we have to interpret that part. So the correlation value is more or less similar to interpret, like your Pearson correlation itself. But the tau, so it is primarily the estimated latent scores. It has taken, it has quantified those variables. So it is trying to map those to the discrete 1, 2, 3, 4, which have been answered by the individuals. So there are 4 cut points. So if the customer satisfaction is below, service satisfaction is below minus 1.83, then he must have given a value of 1. If it is between minus 1.83 to minus 0.72, he must have given a value of 2. And between these two, he'll get a value 3. Between these 4, he is given a value of 4, and then the 5. So that is what it has tried assigning to these customers. And based on that, the correlation has been computed. So this is a slightly different way of analyzing the correlation, especially when we have the ordinal response variables. Much more a better way of finding the relationship between them, rather than trying to do a plain correlation function between the variables. So this is what it is. And just to quickly summarize, these are some of the things that we have taken up quite in detail in this session. We have explored the associations between the variables using the scatter plot. We tried looking at how do we combine the various plots in a single graphic object. Talked about the scatter plot matrices. We used the correlation coefficients and even the graphical ways of plotting the correlation coefficients along with the correlation matrices. And finally, we have spent some time in terms of how well we can understand the associations between the variables in the survey responses that we are typically collecting. So if you have any further queries regarding the same, you can very well get back to me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.